Hi everyone, welcome back to Math 112. This is Scott. Let's get started. What we're going to be doing today is Chapter 7, in which we are going to be bringing triangles back to trigonometry. And the trigonometric functions, as we've studied them so far, have been defined mostly in terms of circles. However, traditionally, they refer to triangles, hence the name trigonometry, which means the measure of triangles. So we're going to start in section 7.1 with right triangles. And a right triangle refers to the fact that it has a right angle, a 90-degree angle. And by the way, for this whole section, we will be measuring almost entirely in degrees. It's very rare that we talk about radians when discussing a triangle, because radians, because as you can tell from the name, have to do with the radius of a circle. So it's always a circle-based approach when we're talking about radians, and a triangle-based approach when we're talking degrees. Okay, so here's the setup. Here's the basic setup for our right triangles. We will have some right angle, which we mark with a little square there. And then we call the side that is opposite that C. And then the other two sides will be A and B. And those two could be switched. No, there's nothing set in stone that makes this A and this B. It could be the other way around. C, however, is reserved for the side that is opposite the right angle. And then you name the angles the same letter as their opposite side. However, when it's an angle, it's capitalized, whereas when it's a side, it's lowercase. So A, B, and C will be our letters, and technically we could call this C if we wanted, and C is always 90 degrees. Okay, now the names for the various parts of this are the hypotenuse, hypotenuse is how you spell that, and then these other two are called the legs. So the hypotenuse and then the legs. And when we focus on a specific angle, then when one angle is focused on, we might call it, for example, theta. Then we again call this the hypotenuse. And then this one is called the opposite angle to theta. Or sorry, opposite side to theta. And this one is called the adjacent side. So the hypotenuse, and then opposite and adjacent sides. Then, here are the tools that we'll have. Tools. So first off, there is the Pythagorean theorem. Pythagorean theorem. So a squared plus b squared equals c squared. One of the most ancient and useful of all of the mathematical results ever discovered. All right, and then another fact is that the angles of a triangle, any triangle, right, or any other, acute or obtuse or anything, angles of a triangle add up to 180 degrees. And then the last tool that we're going to use will be the trigonometric functions. And the way those are defined in terms of the triangle is basically the same as in a circle, just now using triangle language. So sine theta is equal to the opposite over the hypotenuse. Cosine theta is equal to the adjacent over the hypotenuse. And tan theta is equal to opposite over adjacent. And then the reciprocal functions would all just be the reverses of these, but we don't really focus on those so much as we focus on the three primary functions. And then there's a memory aid here. Memory aid. So the mnemonic that is often used for this is SOHCAHTOA. Just as a way to organize your mind, SOHCAHTOA. So this stands for sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and then tangent is opposite over adjacent. So SOHCAHTOA. So that's a mnemonic device that is frequently used to help keep straight the various pieces. All right, now to use any of these tools, what we need are two pieces of information that we can put into play. So to use these, we need to have two pieces of information. We need two pieces of information, and then you just find a formula where those two pieces are involved, and then the piece that you need to find is there. So we need two pieces of information. So find the equation that incorporates the info you have and solve it for what you want. And the general task that we're going to be dealing with here is what's called solving a triangle. Solving a triangle. This refers to taking two pieces of information that you're given and finding all of the other missing pieces. So solving a triangle. Take two pieces of information and find all the rest. Of the sides and angles. All right, to see how this would go, just as an example, we could start with something like this. So for all of these, we're just going to have as our basic layout the usual triangle here. Sorry, so let's say A, B, A, B, right, and C, and then for each example, we'll just have different combinations of the data already given to us. So let's say we start with something like this. So we are told that little b is equal to 4, big B is equal to 10 degrees. Okay, so let's see what we can do here. So we have little b and big B. So we'll just do a quick little sketch here. 4, 10 degrees. All right, so what can we immediately tell? So this is angle A, which we need. This is side A, which we need, and this is side C, which we also need. Now we just need to get the ball rolling by finding the first piece that we can find, and so we could, for example, find angle A. So we know that A plus B plus, and we can call this one C if we want, C equal 180 degrees, and we already know B, 10 degrees, and we already know C, because it's a right triangle, is 90 degrees. And so that means A plus 100 equals 180, meaning A must be 80 degrees. Okay, so that was nice. Now, if I want to find any of the other things, I just have to find the equations that relate them. So let's just say sine of 10 degrees. What's that equal to? Well, that equals opposite over adjacent. So relative to the 10 degrees, the opposite side here is 4 over the hypotenuse. Sorry, it's opposite over hypotenuse. So it's 4 over the c. So then if I solve this for the c, I can multiply both sides by c, divide both sides by sine of 10. And then you would just evaluate this in a calculator. So you would make sure your calculator was in degrees. Always a first step in any trigonometry calculation. Make sure that your calculator fits what you want it to be in. And so we just do 4 divided by sine of 10. So it's 23.03. We will round to the nearest hundredth in all these. So we'll round to the nearest hundredth. That's what your online homework will ask, so that's what we'll do too. Okay, so I got C now. Now, if I want the big C, that one was already known, so that's already known to be 90 degrees. All right, what else do we need? We need the angle. We need the side A. So you can do this now a couple of different ways. You can use the Pythagorean theorem, or you can use another trigonometric function, your choice. My preference here will be to use a trigonometric function because I don't want to use a rounded value if I can help it. I'd rather use an exact value to produce my work. And so I will take the trig function that relates the 4 that I know and the missing piece that I want. So the tangent of 10 degrees is opposite over adjacent, so that's 4 over the mystery A. And so I would just, do the same thing I did, but with tangent instead of sine. So I would multiply both sides by A, divide both sides by tangent of 10 degrees, and so we'll have 4 divided by tangent of 10 degrees. And what is that going to give us? That's going to give us 4 divided by tangent of 10 degrees. Again, just make sure your calculator is still in the degrees, and that gives us 22.68, or 69 if I round it. Okay, and so that gives us our 3 missing pieces. So A is 80 degrees, little a is 22.69. And there's no harm in giving the ones that we already knew as well. B is 10 degrees, little b was 4, and then C is 90 degrees as always, and little c is approximately, these ones are approximate, is approximately 23.04. And then a quick check to make sure this makes sense. The hypotenuse should always be the longest side. So the longest side of any triangle will always be the hypotenuse. And so does that make sense? Yep. All right. Oh, and a note, the little diagrams that we will draw, we will basically never draw them to scale. We'll always just draw them schematically to help us organize our minds what is opposite to what and what is adjacent to what, but we will not be drawing these very precisely or to any kind of accurate scale. All right, so let's see how else this might go. Let's say we have little a equals 7. We have b equals 50 degrees, capital B. Okay, so once again, we'll just start by just drawing it and just figuring out what we have, what we want. Not to scale. Okay, so if this is A, this is B, which we know is 50 degrees. This one will be C, which is the right angle. So this will be little c, which we don't have. Little a we do have. And then over here, this is the little b, which we don't have. Okay, so then we just have to figure out how to connect the pieces we have to what we want to find out. So once again, just look for, so if I want to target something, let's say I want to target the little b, I can just find the trigonometric function that relates the one I have with the one I want. So I can go with the tangent of 50 degrees is equal to opposite over adjacent, so it's mystery b over 7. And then that means that b, if I multiply both sides by 7, would be 7 times the tangent of 50 degrees. Which then again, we just use our calculator. 7 times tangent of 50 degrees is 8.34. Okay? Duly noted. Now, let's say I want capital A. Well, capital A, I already have 2 of the angles in play here, so I'll just use that A plus B plus C all equal 180 in all triangles. This will be the case, right or otherwise. And here, mystery A plus known B plus known C, oops, that's 90 degrees, equals 180. And so, what's that? That's going to be 140. Which means that A must be 40 degrees. Okay, that's nice. Now, what else am I missing? I'm still missing the little side C. So for C, again, I would prefer, I could use the Pythagorean theorem at this point, but I would prefer not to use something that's going to involve having to round any of the ingredients. So once again, I'll just find the trig function that relates them. And in particular, C is the hypotenuse, and I have the adjacent side, and so that would be cosine. So that's going to be 7 over the mystery C. So if I multiply, So if I multiply by c divided by cosine 50, I'll have 7 over cosine 50 degrees for my c, and then that will equal and there are different ways you can go about these. 10.89. So if you were instinctively leaning towards a different approach, that's fine, it probably would work. So capital A was equal to 40 degrees, that one was not approximate. Little a, we did have to, no, little a was given to us, that was 7. Capital B, that was 50 degrees given to us. Little b we found, and we had to round it a little bit, so it's 8.34. And then capital C is always 90 degrees. Little c is equal to 8. It's approximately equal to 8 or 10.89. And a quick check again, the hypotenuse should always be the longest of the sides, and sure enough it is. Okay. One last twist here. Let's say part C. Let's say that what we have are A equals 3, C equals 6. A equals 3, C equals 6. So we have two pieces of information and we just need to get the rest. Okay, so once again, just draw a quick little schematic here. Just decide what you're going to call what. So C equals 6. Okay, so if I decide to call this one A, this one would be little a, this would be B, and then this one would be little b. Now, by default, it might be a good idea to put them in some kind of a regular order that you can always remember, so that you don't mess it up. But once again, this is not to scale. All right, so let's see here. What can I try to find? Well, if I want to find the other side, this is a right triangle, so I am authorized to use the Pythagorean theorem. So, a squared plus b squared equals c squared. So here I have two of the three pieces, so I can solve for the missing piece. So that's going to be 3 squared plus mystery b squared is equal to 6 squared. And so that's going to be 9 plus b squared equals 36. So then that means that that b here, b squared, is going to be 36 minus 9, which is 27. And that means that b is equal to the square root of 27, which it's not really so necessary for us to evaluate this exactly, doing anything too crazy here. But if we did want to evaluate this or simplify this, you could pull out a perfect square of 9. So that's the square root of 9 times 3, which is the square root of 9 times the square root of 3, which equals 3 root 3. Or we can get a decimal approximation. We can get decimal approximations here for all of our answers, because the answer square root of 27 is not very satisfying. Neither is the answer 3 root 3 if we are trying to, I don't know, survey a field. We want an actual number. So let's see here. So 27, or I could evaluate this in the form that it was there, either way. And it looks like it's 5.196, so that would round to 20 if I wanted to go to 2 decimal places. Alright, so that was B. Now if I want the angles, I can find big B by just finding the relationship that incorporates both the pieces of information that I have, and then gives me what I want. So okay, so let's see. Cosine of big B is equal to, and then it's adjacent over hypotenuse, which is just 1/2 here. So then little b, so big B is equal to cosine inverse of 1/2. So if I wanted to solve these, then I have to use the inverse trigonometric functions, and actually it turns out this one is one that's known to us. We actually already know this, but let's pretend like we didn't for a second. So here, the way you'd evaluate this is you use the inverse cosine. So that's so it's going to be second, and then whatever button has the cosine on it on your calculator, of 1/2. And we already know what this is going to be, but let's just make sure. 60 degrees, yep, checks out. That one was known to us from our investigations of the unit circle, but no harm in being cautious. And then if I want the A, so then A plus 60 degrees plus 90 degrees equals 180. So that means that this adds up to 120, so A has to equal what's left over, which is the 30. And it makes sense, a 30-60-90 triangle is famous. Okay, so that's all the pieces. So then we just organize our answer here. A is 30 degrees, little a is 3, B is 60 degrees, little b is approximately 5.20, and then big C is 90 degrees, as always. Little c was approximately, no, not approximately, little c was given to us, it was exactly 6. Okay, now, for applications, what we often want is information about the height of something or the distance for something, and we need a couple extra terms. So first, if we are looking up at something, which is a common way of measuring a height in surveying, then the angle from our line of sight to the object relative to the ground here is called the angle of elevation. And then if, on the other hand, we're looking down, like let's say we're looking into the Grand Canyon or something like that, and we're looking down at something, we call that the angle of depression. And then what we'll just do in all of these, in all of the applications that we'll have, is we just take the information that's given to us, make a triangle, and use that. So let's say, first off, the height of the Eiffel Tower. So the height of the Eiffel Tower. And actually that's spelled wrong. Eiffel, like that, tower. So from a distance of 80 feet the top of the Eiffel Tower has an angle of elevation of 85.361 degrees. How tall is it? Alright, well, let's just sketch that out. So 80 feet is how far from the base we are. equation is told to us that it is 85.361 degrees. And then the question is just the height here. And I'll just use H for height. Or we could use B if we wanted to stay in the more familiar letters. Okay, so then once again we just have made a little triangle here. It's a right triangle because we're just talking about the height from the ground, so straight up. And so we just find the trig function that connects what we want with what we have. And so that's going to be the tangent. And that's equal to opposite over adjacent, which relative to us, the height is the opposite, and the base is the adjacent. So then that means that h would just be equal to 80 times the tangent of 85.361. And then we just can crunch the numbers here and find the answer. So 80 times tangent of 85.361, and that equals 985.91 feet. And this is a word problem. Word problems deserve word answers, so we can say the Eiffel Tower is 985.91 feet tall. Okay. Now, one more thing I want to cover before we leave off this section will just be the standard way that bearing is given in navigation or surveying. Bearing. So the way the direction is given in navigation. So this could be air travel, or on the high seas, who knows. All right, so the way the direction is given in navigation. All right, so the way it works is you start with either north or south, so it's whichever is closest. And then measure the angle off true north or south, and give the direction east or west. It deviates. So for example, just to see what that looks like, so the way these are written would be something like north 45 degrees east. So what that would mean is from a starting direction of north, you deviate 45 degrees in the direction of east. Or maybe it's south 25 degrees west. So that means from a starting direction of south, you deviate 25 degrees in the direction of west. So if we wanted to see what this could be like, so you won't see any of these in your MyLab homework, but you may see it on a quiz. Who can say? So an example would be something like this. You travel 10 miles north, then turn and travel 3 miles west. What is your bearing relative to your starting position? Okay, well, let's just sketch it. 10 miles we went north, followed by 3 miles that we went west. Oops, 3, and that's a right angle. So then the question is, what is this bearing? So where we stand now versus where we started. And so what we need to do is get this. So we want this angle. So this angle A is what we want, and we can just try to figure it out. So A here, we have the opposite side and the hypotenuse. So that sounds like a sine to me. So sine of the mystery angle A is equal to the opposite over the adjacent, over the hypotenuse, which means A is equal to the sine inverse of that, which then would be approximately 17.46 degrees. And then again, a word problem deserves a word answer. So you can say your bearing is, so from the direction of north, you go 17.46 degrees in the direction of west. Relative to the start. So that's how you would answer a question like that. Draw a triangle and then figure out, based on the triangle, which of the formulas this would fit into, and you can then solve for the part that you want. All right. And so much for right triangle trigonometry. So what if, though, the triangle that you're trying to analyze is not a right triangle? Then some of our favorite tools are no longer on the table. So what we need are some alternative tools to help us deal with these situations. So first tool is 7.2, the law of sines. So note, if a triangle is not right, so in other words, no 90-degree angle, then we cannot apply the Pythagorean theorem or our SOHCAHTOA. Our triangle definitions of the sine, cosine, and tangent. So we need alternative tools. So alternative tools must be used. Are needed. And the first one of those that we are going to be talking about here is the law of sines. Alright, so here's the setup. What we've got is just a general triangle. A, B, C, little a, little b, little c. So not a right triangle. Then what we can apply are some known facts. So here is the law of sines. So sine A over little a is going to be the same as sine B over little b. And by the same token, sine A over little a is the same as sine C over little c. And by the same reasoning, sine B over little b is the same as sine C over c. Oops, over c. And so these are all basically actually the same equation, just changing our choices of A's, B's, and C's. And then alternatively, we can also write A over sine A equals B over sine B, etc. All right. To use this, what we need are three pieces of information. We need a matching pair of side and angle, and then one other piece to use this. So we need fill in 3 of the 4 quantities in one of the equations. Then we solve for the fourth one. So in other words, we need a matching pair, angle and side, plus one other, either angle or side. So that's very good when it works. However, there's a warning. Warning. When using the law of sines to find an angle, we will often encounter an ambiguous case. And that ambiguous case refers to the fact that the information that we have been given may be consistent with two different triangles, or possibly it's not consistent with any triangle at all. So there are 3 possibilities. Possibility 1. 2 different triangles are possible. So this is the worst case. The worst case we can imagine. So we have to actually solve the triangle twice, once for each possibility. And this is it comes from the fact that when we use the inverse sign, it will only tell us one of the possible answers, and we have to figure out the other one. So how this comes up is when we use sine inverse, it will only tell us about the angle that's less than or equal to 90 degrees. If there's an obtuse possibility and an obtuse angle, and an obtuse angle means an angle that's more than 90 degrees, i.e. we have to find it ourselves. We have to find it by taking the supplementary angle. So that's 180 minus our angle. And the reason for this is that if you think about if I just tell you the sine of an angle, it could easily be the angle in quadrant 2 that we could be referring to. So these have the same sign. And if this is theta, this would be 180 degrees minus theta. So we always have to consider this possibility when we are using the law of sines to find an angle. Not when we're finding a side, but when we're finding an angle. Okay, so that's possibility 1. Possibility 2. One of the two triangles is impossible. So it's possible. So we might encounter the case where one of the two triangles is impossible. That leaves us just one option. So this happens when the obtuse angle would be too big. And there are two ways to tell if it's too big. Number one, maybe it causes the angles to add up to more than 180 degrees. So either the angles now add up to more than 180 degrees, or the larger angle would correspond to a smaller side, which isn't possible. For a triangle. So if you think about it, the biggest sides always have the biggest angles, and the smallest sides always have the smallest angles. So bigger sides have bigger angles. So if you think about it, any triangle you choose to draw, that will always be the case. So that's possibility 2. So maybe one of the two triangles that we would be considering is actually not an option. And then possibility number 3, maybe no triangles are possible. So no triangle is possible. Okay. And this would just come from, again, violating one of those two principles. So this mainly happens when larger angles would have to correspond to smaller sides. Okay, so enough talk. Let's actually see how this would actually go in practice. So let's start doing some examples of these. All right, so let's just say, so solve. The triangles, and here A, B, C, no particular order, little a, little b, little c, and these triangles will not be drawn to scale. They're just a schematic diagram. And let's just say that what we've got is something like this. So A. So let's say what we have is capital A is 40 degrees. Capital B is told to us to be 20 degrees. And then little a is told to us to be 2. Okay, so let's just see what we can figure out. So first off, C. A plus B plus C still equals 180 degrees. So that means 40 degrees plus 20 degrees plus whatever's left over for C is 180. So what's that make? So 60. So that means C equals 120. Okay, so be it. We didn't have to use the law of sines to find that, which is nice. You never want to be in the case where you have to use the law of sines to get an angle. Sometimes you have no choice, but it's not pleasant. Okay, so now if I want to find a little one, let's say a little b. So I can use the information that's given to me. I've got 3 out of the 4 pieces to fit the equation sine a over little a equals sine b over little b. So I've got 3 of the 4 pieces, I can put them into play. Okay, so that means sine of 40 degrees divided by 2 is equal to the sine of 20 degrees divided by b. And if I want to solve this, the easiest thing would be to, say, cross multiply them and then divide. So multiply both sides by 2 and by b. And then divide both sides by 40 degrees. By sine of 40 degrees. Okay. So this, by the way, is why sometimes it's to your advantage to write the whole equation with the little letters on top and the angles on the bottom, because then it saves you like one step. All right, but then we again just plug this into a calculator and ask it. So 2 times the sine of 20 degrees, careful to end the parentheses, divide by the sine of 40 degrees. And that gives us 1.064, and we'll just round it to 2 decimal places. That'll be our custom here. Okay. And then what's left? Little c. So for little c, once again, we have the 3 pieces that we can put into play for the sine a over a equals sine c over c. So here, once again, sine of 40 degrees over 2 is equal to sine of 120 degrees over c. So once again, we were finding the sides using the law of sines, so there's no need for any ambiguous case considerations. So we just do the same thing we did, multiply both sides by c and by 2 to cancel the denominators. So c sine of 40 degrees is equal to 2 sine of 120 degrees. And then divide by the sine of 40. And technically, we know the sine of 120, actually. That one is one of our known angles. But since there are other parts here that we don't know, we might as well just go ahead and put everything into our calculator. So 2, and it's the sine of 120 this time, divided by sine of 40. And I get 2.69. And those are all 3 of the missing pieces, so let's just sum it all up, including the pieces that we already knew, just to make a nice little organized answer here. A is 40 degrees, little a is 2. Big B is 20 degrees. Little b was 1.06 approximately. And then finally, big C, which we could tell from just the A and the B here, must be 120, and then little c, we had to use the law of sines, and that was 2.69. Okay, so this is a case of finding a missing sides by using the law of sines. That's by far the easier of the cases. The harder of the cases is when you have sides given and you need the angles. So here's an example of something like that. So let's see. So these will lead us to the ambiguous cases. So let's say that little a equals 3, little b equals 2, and then capital A equals 50 degrees. Okay, so that's the information that we're going to be given here to start. And let's just see what we can figure out. Okay, well, first off, I can find the big B by using the law of sines. I've got 2 two pieces for the A and then one piece for the B. So then I can say that sine A over A equals sine B over B, and I can solve this for the B, the one part that I don't have. Okay. So sine of 50 degrees divided by 3 is equal to the sine of our mystery B divided by 2. And if I'm solving this for the B, I have to move everything over. So what I'll have is, so sine B, I'll write that on the left, is equal to, and I just multiply both sides by 2. And that's going to be 2 sine 50 degrees over 3. And I'll just leave it like that, and then I'll say B is equal to sine inverse of that. And this will be the first of the possibilities to consider. And we'll evaluate that and see, and then consider the other possibility. So sine inverse, that's again second and then the sine. 2 sine 50 degrees into the sine, divide by 3 into the sine inverse. So that's going to be 30.71 degrees, or maybe 180 minus 30.71 degrees. So we have to at least consider this possibility. So minus the answer. And that's going to be 149.29. Okay, so let's see, is that possibility viable? So looking at the angles that we have two possibilities for B, 30.7 or 120 or 149.29. Now, is this one actually possible? Well, considering the A that we already have, this one would be too big. This is too big. So this case is not ambiguous. There was only one possibility, because there's no way for our triangle to add up to more than 180 degrees, and so we don't have enough budget for a 149.29 degree angle. That's too big, so not a possibility. Okay. Also note that this would make the angle for B bigger than the angle for A, even though B is a smaller side. So again, not possible. Okay, well then we can proceed. So then C is equal to, well, we'll find C now. So we only had this one case, and so we have A plus B plus C equals 180. So that's 50 degrees plus 30.71 degrees plus C equals 180. And so if I subtract them, I'm going to get C is equal to, I guess, approximately, since B was approximate. And C would be approximately, so 180 minus 50 plus 31. That's 30.71, and that's equal to 99.29. So be it. And again, these should all add up. And based on this, we know that side C is going to have to be the biggest side of all, but we'll let the law of sines decide that for us. So then for little c, again, we'll take the pieces that I have and put them into this little array. So sine of big A over little a is equal to sine of big C over little c, which here is going to mean sine of 50 degrees divided by 3 is going to equal sine of 99.29 degrees divided by little c, multiply both sides by the two denominators. And then divide. And that's going to give us our answer here, which is going to be 3 sine 99.29 divided by sine 50, which is going to be 3.86 if I round to the hundredths place. All right, and then that's the whole triangle. So we have big A was 50, little a was 3. Those were given to us. Big B was not given to us, but we know it. It is 30. It's approximately equal to 30.71 degrees. Little b is approximately equal, or no, is exactly equal to 2. Big C is approximately equal to 99.29 degrees. Little c is approximately equal to 3.86. Okay, so this was a case where we considered two possibilities, but one of them turned out to be impossible. Okay, so now let's try something like this. So that was example B. Example C. Let's go with B equals 4, little c equals 5, and then capital B equals 95 degrees. Okay. Now, right now, I'm already suspicious about this because little b is more than 90 degrees, so it has to be the biggest angle. It can't have another angle bigger than it. And yet side B is not the biggest side. This shouldn't work, but we'll just let the math speak for itself. So if I want to find first angle C here, I would take the sine of B over little b, and that's equal to sine of big C over little c. So here that's sine 95 degrees divided by 4, which is equal to sine of our mystery angle divided by 5. So then I would multiply both sides by the 5 there. And so then I'd have sine C is equal to 5 sine 95 over 4. And then that means that C is equal to sine inverse of that or maybe something else. So let's always keep the possibility open. Whenever you see a sine inverse in one of these, you have to keep an open mind to the possibility that there's going to be a second answer. So sine inverse, 5 sine 95 divided by 4. Let's just see what we get here. Domain error. Domain error. What does that mean? What that means is we tried to take the inverse sine of something that was not in the domain of the sine inverse. So that means this number was bigger than 1, which means that this is impossible. So we could have actually, if we were being very observant at the very beginning, we might have known that this was a hopeless case because our little b is smaller than our little c, but there's no way for angle C to be larger than angle B. So this is an impossible triangle. All right, and now let's see what it looks like when we have the other of the ambiguous cases. So the next example here is going to be little b equals 2, little c equals 3, and then capital B is equal to 40 degrees. All right, little b is 2, little c is 3, big B is 40 degrees. Okay, so let's just see what we can figure out here. So the very first thing to note is that we have all the ingredients in place to find big C, which is bad. Bad news for us because it means using the law of sines to find an angle, which means the possibilities of badness are present. Sine C over little c is equal to sine B over little b. So, okay, sine C over 3 is equal to sine of 40 degrees over 2. So solve this by multiplying both sides by 3. So 3 sine 40 degrees over 2, which means then that C is going to equal the sine inverse of that, or 180 degrees minus whatever we get. So we just got to consider these as both possibilities. Okay, let's see what happens. So sine inverse 3 sine 40 degrees divided by 2. Gotta be careful about your parentheses on these, otherwise you might get an error of an unexpected nature. So this produces an angle of 74.62 degrees. All right, now let's consider the possibility, 180 minus that. So then what's that? That's going to be 5.38, or sorry, 105.38. All right, can this possibility be rejected off the bat? It cannot. So this is totally consistent with the information that we have so far. So there's no reason not to take this seriously. Okay, so be it. Well then, what's that mean for capital A? So in this case, so there are two triangles. There are two triangles that are going to emerge, and we're just going to have to follow each one down its course. So A plus B plus C equals 180. And so then that means that the mystery of the big A will be that it plus 40 plus 74.62 degrees equals 180. And then that means that 180 minus 40 minus 74.62. That means it's going to equal, A is going to equal 65.38. Okay, so be it. And these are all approximate again. Once I have started the business of rounding, then it is, then all of my answers are going to be only approximate. And then alternatively over here, A plus B plus C still is going to equal 180, but we now have a different information for C. So A equals 40 degrees plus now 105.38 degrees is equal to, is approximately equal to 180. So then that's going to add up to 145.38. So it's going to be 44.62 degrees. Okay. Well, if there are two possibilities for big A, then that means that there are going to be two possibilities also for small a, for the side. So now to find little a, it's going to involve the law of sines, and we look at what we have the ingredients for. Looks like I can use the b and the a. So sine of a over little a is equal to sine of b over little b. All right, and the information that we have says sine of 65.38 degrees divided by the mystery of the little a is equal to sine of 40 degrees divided by 2. So now we just solve this, cross multiply. A sine 40 divided by sine 40. Two sine 65.38 degrees divided by sine of 40 degrees. And before I calculate that, it will go the exact same over here. So we're in a parallel universe where the c was equal to another, the capital C was equal to a different value, and so therefore was the capital A, and so we have to do the whole calculation again with the new value of capital A. So the new value of capital A was 44.62 degrees divided by little a, sine of 40 degrees over 2. And so again, the exact same process will lead us to exactly the same sort of a solution here. And so a would be, on the other hand, 2 times, so we're just dividing by 40 again, 2 times the sine, 44.62 degrees, divided by sine of 40 degrees. Okay, so let's see what this will make. So that means that 2 sine 65.38 divided by sine of 40. So that's me just entering in what it says there. And that gives me 2.83. Versus, on the other hand, same calculation. If your calculator lets you, you can just scroll up and make a little discrete change to your number so that it fits the new one. 44.62 instead of the previous number. Same calculation up. And it's going to be 2.18 or 19. So these are similar answers, but they are different. Now, if you want to know what's going on here with this, basically the picture here is that that we have these two different possibilities, and it would look like this. Okay, so we'll start with B. So B is 40 degrees, so I'll draw that roughly. So then if I knew and then this side over here was known to be 2, and then basically actually here. So let me try to draw this better. Okay, so what's going on here is we have 40-degree angle, and then we have a known side of 2, which could correspond with either being there or there, and then these are the two A's. And then this over here is, and then this over here is capital A, which is one of those two values, either the bigger or the smaller. And then over here is obviously the side C. So we have two different possibilities. Two different triangles can emerge here. All right. So then the two possibilities were A equals 65.38 degrees, little a was 2.89 or 83. Big B was 40 degrees in both cases. Little b was 2 in both cases. Big C was equal to, on the one hand, 74.62 degrees. Little c, on the one hand, was equal to, C is equal to 3 in both cases. Or the A was the other one, 44.62. Little a was then 2.19. B is 40 degrees and 2. Capital C is equal to 105. 0.38 degrees, and little c equals 3. So this is what it looks like when we have the ambiguous cases. All right, now let's see an application. So in an application, the most important thing is if you just draw it properly, you can, you're halfway there. So let's just try an application of this. And we'll see how the law of sines is frequently used in surveying. So let's say that we have, a ski lift, and we measure it twice from 2 different points, and we want to find out the distance from the base to the height. So okay, so let's say we've got an angle going that way, an angle going this way, and say this is point Q. This is point P, this is point R, PQR, and then let's say that this is 15 degrees, and let's say that this angle of elevation is 25 degrees, and the question might be, how far is it from P to Q? Okay, so let's think about what we are really wanting here. So we want that side, and if we want to name these according to regular notation, the points, which will also be the angles, will be capital, and then the lowercase ones will represent the sides. So really what we want is R. What we have is big R is equal to 15 degrees. We can see that already. Now, big P, on the other hand, is not directly given to us here. Oh, sorry, and I need one more piece of information. Let's say this is 1,000 feet. Okay, so we know little q is equal to 1,000 feet. And then big P, so the angle that's been given to us here, the angle of elevation, is not actually the same as big P. It's actually the supplementary angle to that, so 180 minus 25, which is going to be 155 degrees. And so now we just need to figure out if we have the information that is necessary to use the law of sines. So far, the answer is no. We can't use the law of sines yet. We don't have a matching pair of letters with of angles with sides. However, Q is going to be 180 minus the 15 minus, again, the 155, since P, Q, and R all have to add up to 180 degrees. So that's 160, so that means that's going to equal 20. Or sorry, it's 170, so it's going to equal 10 degrees. So Q is 10 degrees. So now we can use the law of sines. So the law of sines, the way that works, just take matching pair. So Q and Q. Sine of Q over little q is equal to sine of big R over little r. Little r is the one we want. R sine Q is equal to Q sine R. Okay, well then that means that R is equal to Q sine R over sine Q, which would be, in this case, 1,000 feet. I'll leave the units off until the end. 1,000 sine of 15 degrees divided by the sine of 10 degrees. And so then we calculate 1,000 times sine 15 divided by sine of 10. So I just entered it in as I said, and I get 1,490.48 feet. So 1,490.48 feet. So feet long. So that's how long the ski lift is. So if P is where the ski lift starts, then that's how long it is. So that's how you can use the law of sines to answer a question essentially from surveying, which would give you then the height of something based on two measurements of two different angles and the distance between them. Alright, and that is 7.2 for you. Now, if we look back at it, what we did in 7.2 was basically the non-right triangle adaptation of SOHCAHTOA. What we're going to see here is the non-right triangle adaptation of the Pythagorean theorem, and it's called the law of cosines. So, the law of sines is basically an adaptation of SOHCAHTOA for non-right triangles. What we're about to learn now is the adaptation of the Pythagorean theorem. It's called the law of cosines. So, if we have our usual setup, A, B, and C, little a, little b, little c. The important thing is just that the same letter is used for the angle and the side, just capitalized for the angle, lowercase for the side. So if we have this, then a squared plus b squared equals c squared. Sorry, actually let me rewrite that in the other order. I meant to say c squared equals a squared plus b squared. If I stopped right there, this would be the Pythagorean theorem, and it would just be a right triangle. If it's not a right triangle, you need an extra term, minus 2ab cosine c. But one of the beauties of non-right triangles is then there isn't a specific side that is the hypotenuse. All sides are pretty much in the same position, and so the same thing can be true if we say a squared equals b squared plus c squared minus 2bc cosine c, cosine a, whatever that is must match that. And then on the same logic, b squared is equal to a squared plus c squared minus 2 ac cosine b. And then we can also solve for the angle, and if we do that, what we would get would be this. So we'll just take the top one there, c squared, a squared plus b squared minus 2ab cosine c. And I'll just move this term over, subtract that term over there, and so it's going to be 2ab is equal to a squared, 2ab cosine c. 2ab cosine c is equal to a squared plus b squared minus c squared. Then divide by the 2ab. A squared plus b squared minus c squared all over 2ab. And then that means that c is equal to cosine inverse of that. And by the same token, we can rewrite this with any of the other angles in place of the c, and then the way it scrambles these is basically whatever angle that is, it's that side there. Other than that, everything's the same. So b squared plus c squared minus a squared over 2bc. Cosine inverse. And then here again, a squared plus c squared minus b squared over 2ac. So one of the great things about the law of cosines is that it never produces the same ambiguity that the law of sines does. So whenever we can use the law of cosines, it's going to work out nicely. When can we? So when we can use this. So we can use this anytime we can fill in 3 of the 4 spots in the equation. And to do that, what we need is we need 2 sides and either the angle between them or the other side. So basically you have to have something for each letter. Something for each letter. Okay, and a note. The law of cosines never produces an ambiguous case. The reason for that is that the range of cosine inverse is actually already 0 to 180, not negative 90 to 90. And so it never will be the case that the inverse cosine will fail to tell us the angle. All right, so to use this, you just got to figure out when you can, and then you just plug in 3 values. Solve for the missing one. That's the way to do a law of cosines, and let's see what an example of this might look like. So example, solve the triangle. So the kind of default setup here might just be you just have something like this. Maybe you've got a 4, sorry, let's make that one a 10, make that one a 4, and then you've got an angle here, and let's say that angle is known to be equal to 95 degrees. And then the pieces that we don't have, let's say those are B and A and little c. Okay, let's start by finding what we can find. So let's find little c to start with. So to find little c, we will just use the version of the law of cosines that has the one you want to solve right on the outside there. So it's going to be 10 squared plus 4 squared minus 2 times 10 times 4 times cosine of 95 degrees. So that means that c is just going to equal the square root of all that. Now I'll just go ahead and write it like this and let my calculator do the hard work. we never really consider the negative possibility here. We are not interested in negative sides of triangles. So, square root of 10 squared. I'm just going to enter it as you see it. So 10 squared. You can do a power of 2 like that, or you can also do that by doing, most calculators have a square button. You say x squared. It's supposed to be a plus, and then minus 2 times 10 times 4 times cosine 95 degrees, and this is all inside the square root, remember. And it equals 11.09. So, that's nice. Now, I want the A and the B, and I can do them either with the law of sines or the law of cosines. And whenever I have the choice of either of those two laws, I will use the law of cosines because it's never ambiguous. So for A, capital A, and we just remember there's a case for this too. Cosine inverse of, and then it's just the other two sides. Sorry, it's the C that we just found. 11.09 squared plus the 4 squared minus a 10 squared, all divided by 2 times 11.09 times 4. The only danger here is parentheses. You might end up with some bad parentheses if you are not careful. So let's just see how this goes. Cosine inverse of. Now I want this to be the cosine inverse of the whole fraction. I'm going to be more careful with parentheses than usual because I don't want to mess this up. 11.09 plus 4 squared minus 10 squared. End the parentheses for the numerator. So I put the whole top of the fraction in parentheses. Divided by 2. I want the whole bottom of the fraction to also be in parentheses. 2 times 11.09 times 4. And that ends the denominator, and then this ends the inverse cosine. And I get 63.93. And this triangle was drawn roughly to scale, so we can use it. We can use this number to or we can use the triangle as a guide to see if this looks reasonable, and indeed it does. And then for the B, I could actually repeat the process, or I could use the known values for the other two angles. So A plus B plus C equals 180. So that means that 63.93 degrees plus the mystery B plus the 95 degrees equals 180. So if I subtract both of these over there, it's going to be, so that's going to be 85 minus 63.93. So it's going to be B is equal to 22 or 21.07. Yeah, I better be careful here. Don't be a hero. Just use a calculator. Minus 95 minus 63.93. 21.07. Alright, so there we have it. The three missing pieces. So if we want to sum it all up, what do we know? We know A, capital A was approximately 63.93 degrees. Little a was equal to 10. Big B was approximately 21.07 degrees. Little b was given to us as 4. Big C was given to us as 95 degrees. little c we found was 11.09. So that's how the law of cosines works. Now, let's try another one here. So example B. Let's have one where now we're given all three sides. So let's say this side is 12, this side is 9, and this side is 6. All right. So then I'll call these A, B, and C, just arbitrarily. Just made up the which one I was going to call which. Okay, now it's the three angles that we want, and so we'll just use the corresponding formula, so cosine inverse of. All right, so if it's A that we're talking about here, then it's going to be 9 squared plus 6 squared minus 12 squared, all divided by 2 times 9 times 6. And by the same token, B is going to be cosine inverse 6 squared plus 12 squared minus 9 squared, all divided by 2 times 6 times 12. And that's going to equal whatever it's going to equal, and then we'll just use those to find the C. Alright, so cosine inverse of. Now, careful about our parentheses. Oops, not that careful. Parentheses for the whole numerator. 9 squared plus 6 squared. Nine squared plus 6 squared minus 12 squared divided by parentheses, very important, 2 times 9 times 6. And that equals 104.47. Does that make sense? In the context of this, yep, looks good to me. 477, so really 48, I'll round it to 2. Same thing for B, I'll just go up and take my previous answer and switch some of the numbers around. So instead of 9 squared plus 6 squared, it's 6 squared plus 12 squared. Careful when you make a change and it has a different number of digits, use the insert button so it doesn't mess up all of your next symbols. Minus the, not 12 anymore, but 9 squared. Divided by 2 times, now it's going to be 6 times 12. And that gives me, for B, 46.57 if I round it. And that again looks pretty good. Looks like what B would be. I drew this again roughly to scale so you can use it as a sanity check. All right, and then to find C. So 104.48 plus 46.57 plus mystery C is 180. So I'll just say 180 minus 104.48 and minus again the 46.57, and that gives me 28.95. Alright, and those are the three pieces. So A was approximately 104.48. Little a was given to us. as 12. B is approximately 46.57 degrees. Little b was given to us as 4. Big C was 28.95 by our calculations. Little c was given to us as 6. And now one last little note on this before we look at some examples or some applications. So note, the only time you will encounter an impossible triangle when using the law of cosines is when the longest side is longer than the sum of the other two. So, sum of the other two. Sorry about that. The only time you encounter an impossible triangle when using the law of cosines is when the longest side is longer than the sum of the other two. And what that means is, essentially, your triangle doesn't fit together. So if I told you that A equals 15, little b equals 5, little c equals 8, this would be an impossible triangle. Try to draw it. You have a 15 side and an 8 side and a 5 side, and there's no way to draw those so that they wouldn't join up. They wouldn't link up. So this would be this would be impossible to draw, and then the way the law of cosines would show you that is if you went around trying to find A, that would be a cosine inverse of 5 squared plus 8 squared minus 15 squared divided by 2 times 5 times 8. Let's see what that would give you on your calculator. So it shouldn't give us anything because this is impossible, but let's see what happens. So cosine inverse, careful about the parentheses, 5 squared plus 8 squared minus 15 squared, all divided by parentheses 2 times 5 times 8, parentheses. And we get a domain error. We are looking for an impossible triangle. Alright, so this is the kind of impossible triangle you can find with the law of cosines. Alright, now let's see an application of the law of cosines. So first off, when it comes to distances at sea, so the unit that's used there is nautical miles. So quick note, distances at sea are measured with nautical miles. 1 nautical mile is approximately equal to 1.15 statute miles, which is regular miles. The reason originally why these were the units is because a nautical mile is 1 minute of the arc for the Earth's surface. But that's not really what matters to us now. What matters to us is just to know that that's the unit and a knot. So knot is a measurement of speed. And 1 knot is 1 nautical mile per hour. Okay. So with that out of the way, let's have an example. So let's say a ship is traveling to a destination that's 800 nautical miles away. Let's say the ship travels 20 knots. All right, now here's the situation. In order to avoid a storm, the ship goes off course by 15 degrees. The ship goes 15 degrees off course for 10 hours. Now the question is, what angle should the ship turn to head directly for its destination towards its destination, and B, how long? Will it take to arrive? Okay. And this is after the turn. So after it turns. Okay, so let's try to figure this out. So first off, so let's say we have the ship. It goes from its starting point, which is A, and the destination is B. We know that that is 800 nautical miles apart. Now we know that the ship did not go along this path. Instead, it went 15 degrees off, which I'll exaggerate it in order to make it more visible. So this is 15 degrees. And then it turns to go back to its original course. So this is the turning point. All right. So first off, we need to figure out how far has it already gone along its original course here, along the course that it started off going. So that would be distance B. We'll call this distance A. And then if I call that angle C, that's what we're trying to discover. Okay, so first off, B is equal to its speed times its time. So that's 20 knots times the 10 hours. So that's distance equals rate times time. Okay, so that's easy, 200. So B equals 200. All right, now the question is what angle we should turn in order to get back on course. And so what we're going to need to do is find out the things that we need in order to apply one of our tools. So if we look at what we've got here, we do not yet, in fact, have the immediate ability to answer the question of the angle. We have to actually first find side A. So we'll find side A to begin, because we need to have, in order to find an angle, we need to have the sides around it, according to the law of cosines, and then one other piece of information, like the side against it. Now, if we wanted to use the law of sines, we would still not be able to do that because, again, we don't have a matching pair of angle and side to work with. Okay, so to find A, we would just use the law of cosines. So A squared is equal to 200 squared plus 800 squared minus 2 times the 200 times the 800 times the cosine of the angle between them, which is here 15 degrees. Okay, so then that means that A itself will be the square root of that. And we will just use technology to answer that question. All right. So A will be the square root of and it is 200 squared plus 800 squared minus 2 times 200 times 800 times cosine of 15. That ends the cosine, that ends the square root. And so we get 609.02. And this was nautical miles. Not that that's directly relevant to our calculation here, but good to know. Okay, now angle C. We now have all three sides of the triangle, and so angle C we can now find by using. So let's look at the diagram again. by using the formula for the angle from the law of cosines. So that's going to be cosine inverse of, and then up here are going to go the two sides that are around the angle. So that's going to be 609.02, which we just found, squared, plus the other side, which is 200 squared, minus, and then the final side, which is 800 squared, all divided by, and then 2 times 609.02 times the 200. And again, the hardest part on this is making sure that we get our parentheses all correct, so let's see how we enter it. So, cosine inverse. Cosine inverse of, parentheses for the whole numerator, 609.02 squared plus 200 squared minus 800 squared into the numerator, divide, parentheses for the whole denominator, 2 times 609.02 times 200 into the denominator and end the inverse cosine. And so we get 160.12 degrees. Okay, so now we can start answering the questions. So 160 degrees is what this angle is supposed to be, but that's not actually how we would usually describe a turn. So if we look in the situation of the boat here, so it was now going this way, and this is 160.12 degrees, and so this is the turning angle. The angle of the turn, and so that is going to equal 180 minus, so it's the rest of the straight angle here, 160.12 degrees. And so 180 minus 160, 60.12 is 19.88 degrees. So for part A, the ship should turn 19.88 degrees back towards the destination. And for part B, we have a distance that we know we need to travel. So we need to go 609.02 nautical miles at 20 knots. And so again, so time is equal to distance divided by the rate. And so the time would be 609.02 divided by 20. And that will tell us 30.451 hours. And if we wanted to convert that to hours and minutes, we would take just the fraction part of that, so the 0.451 times 60, and that would be 30 hours, 27 minutes, plus a little bit of extra, which we could even figure out in seconds if we wanted. So the ship will reach its destination after 30 hours and 27 minutes. And then, just for the record, if it had gone completely straight, that would have been 80 divided by 20, which is 40 hours altogether. So in other words, so this is the answer to part B, and so what that means is diverting around the storm like this caused the trip to last an extra 27 minutes. So the trip is 27 minutes longer than it would have been if we didn't turn to avoid the storm. So that's just an interesting side note, not necessarily what was asked, but it's good to know. So going 15 degrees out of our way for 10 hours ended up adding 27 minutes to the total trip. All right, well, that's just one example of how you can use the law of cosines. For the most part, though, in general, using the law of cosines is pretty straightforward once you have identified the triangle that you should be using. So step one is always try to draw the triangle and work from there. All right, well, that's going to do it for this epic episode of Math 112. I'll see you next time. Bye.